So this is the third lesson to section 4.2, dealing with experiments. Today's lesson is going to be dealing with the placebo effect, but also talking about statistical significance, and we're going to do a simulation, or we're going to try to do a simulation. If you don't have cards, then you can just really just kind of watch this video, and then I have saved some data from previous simulation so that you don't really have to have a deck of cards to do it. We're just really going to, just be fun to actually collect some data if you want. But we're not really going to do that today, since this is just, you're watching a video, but you'll see how we would have collected that data, or how we collected it in years past, because I just saved some data from a previous year, and I'm showing that in one of the last slides. Okay, so as you can see here, this lesson is dealing with the placebo effect and blinding of experiments, and we'll talk about what that is in a couple of slides. And then the meaning of statistical significance. So basically that is, how likely is this to have occurred just by chance alone? If it's not very likely that we would get the results that we got in an experiment just by chance, that means that the results are statistically significant. All right, so when we do a randomized comparative experiment, the logic is to, first of all, treat everybody the same. So we want to minimize the confounding of variables, which we've talked about previously. We want everyone to be treated exactly the same. We want both treatment groups to be as identical as possible. And so then the only difference between the treatment groups will be the treatment. And so if we find that there is a difference between those treatment groups in the response variable, whatever we're measuring, then we can be pretty certain that the difference in the response variables between the treatment groups has been caused by the actual treatment. Okay, so we want to be careful. We want to pay attention to detail. We want to make sure that everyone is being treated exactly the same. All right, the response to a dummy treatment is called the placebo effect, and often we'll refer to that dummy treatment as a placebo. Now, a placebo is simply just a treatment that is indistinguishable from another treatment, the actual treatment. In other words, if I'm giving I'm doing an experiment on headache medicine, and one group is getting the new improved pill, the other group would be getting an identical looking pill, but it's what we call like a fake pill. It's like a sugar pill. All right, so it has no actual active ingredients in it, but we need to make sure that we're controlling for what's called the placebo effect. So in other words, if people are in an experiment and you're doing something like a headache medicine, people will feel better just because they think they're getting some kind of treatment. And the treatment that we give them, the new headache medicine, may be completely useless. It may not do anything, but people will still feel better. And so we don't know if people are feeling better because the new treatment is actually good, or if they just think they feel better because they're in this experimental, they're getting this new experimental drug. So it's hard to tell whether the decrease in headaches is caused by this new improved medicine, or the effect that people just feel like they're doing better because they're getting some kind of pill. So you give some people a placebo, and some groups, treatment groups, a placebo, and the other treatment group this new pill, and then we can decide whether or not, is there a difference? Like, everybody's part of the treatment, is part of like what they think is a treatment group. And so we can look at the difference between people who are just feeling better because they're in an experimental treatment, which really in this case is nothing, right? It's the placebo, but they still feel better. And so we can look at the difference between those people's response and the people who are actually getting the pill, the real pill. And that is basically the difference is referred to as the placebo effect. All right. And so, yeah, so the reason that we use a placebo is simply because we want to be able to tell the difference between people feeling better because they think they're going to feel better and whether or not they feel better because the new drug is effective. All right, so double blind. So we talked about blind experiments. Blind experiments just mean that the people who are the subjects, the people who are getting these treatment, don't know if they're getting the real treatment or if they're getting a placebo. And then a double blind experiment just means that neither the subjects nor the people interacting with them know what treatment group they're in. So in other words, you come by once a month for your bottle of pills. I'm handing them out to you. I'm interviewing you. I might be asking you questions. How are you feeling? And taking data from you. But as I'm handing you this next month's worth of pills, I myself don't know what's in those pills. I don't know if it's the real thing or if it's the placebo, because I might interact with you differently if I know, oh, this poor person who's sick isn't getting the real pills, and I might interact with you differently than if I just don't know. And so that's why we use double blind in experiments, especially when we're dealing with experimental treatments. All right, so here we go. This is really the real essence of statistics is this inference. So we want to see what the result is and can we infer that back to a bigger population. And so we want to know if the results we get, the difference in the response from the two treatment groups, whether that is statistically significant or if that could have happened just by chance alone. So we would expect people with the new headache medicine to feel better and not have as many headaches as people who are getting the placebo. But, if there's just a slight decrease in the number of headaches, that could just happen just by chance, right? One group might have more headaches than another. And so if we think that the difference in the response variables is big enough to have not occurred just by chance alone, then we call these results statistically significant. Okay, so an observed effect or change in the responses between the two treatment groups is so large that it would rarely occur just by chance, then we're going to call that statistically significant. And the threshold that we use typically is 5%. All right, so, and then last thing here is statistically significant association. In other words, when we see like, okay, people who got this pill felt better, people who did not get this pill did not get better, because we got those results from a well-designed randomized experiment. It's not only just an association, but we can imply causation. It's the only time we can do that. We have to run an experiment in order to show causation. All right, so let's look at this idea of statistical significance in the context of an example. And we don't know how to calculate probabilities yet related to these situations. We will in later chapters. But so for now, what we're going to do is we're going to simulate this and come up with how likely is this to have occurred just by random chance. And so our simulation is going to be just based on random chance, see how often we get the same results or results that are more extreme. And then we'll be able to determine hopefully whether we think the results are statistically significant. All right, so here's the situation. 48 subjects are randomly assigned to one of two treatments. They're driving in a simulator. You've seen these in the movies. I don't think we have these at the high school. I think we might have some kind of simulator, but it's a simulator that makes you look like you're driving, right? There's a screen in front of you and you're driving, and the screen changes as you drive. Like if you've seen like Peloton while you're riding your bike, you can be going through the streets of Paris, whatever. So same kind of thing. So anyway, so the 48 subjects are randomly assigned to drive a simulator while either talking on their cell phone or talking to a passenger sitting next to them in the simulator. Okay, their assigned tasks. Their assigned task is that when they're driving down the highway and they see a rest stop, that they're supposed to pull over into the rest stop and come to a stop. And so that's their task. And we're going to keep track of how many people, as they go down the highway, who are talking on the phone, how many people stopped versus how many people stopped when they're distracted by a passenger. Okay, so is a cell phone more distracting than a passenger? So you can see we have 24 people in each column, and you can see in the cell phone group of 24 people, 12 people actually did stop. They noticed this, while they're talking on the cell phone, they noticed that they had come up to the rest stop, pulled into the exit for the rest stop, and had stopped at the rest stop. 12 people did not do that. And then if we look at the 24 drivers who had a passenger next to them, 21 of them stopped versus the 3 people in that group did not stop. So it kind of seems like there's more people stopping when it's just a passenger next to them distracting them rather than when people were talking on a cell phone. All right, but is this difference enough so that we can say it's statistically significant? And so, in other words, how likely are we to get a difference in that ratio of fail to stop? So in the cell phone group, half the people failed to stop. In the passenger group, 3 out of the 24, or 1/8 of the passenger, 1/8 of the drivers failed to stop. So how would we expect this to happen by chance? Like, what's the probability we would get a difference this big just by chance alone? All right, so what we're going to think about is the following. Those 15 people who failed to stop, we have to assume that there is no effect here. That's talking on a cell phone versus talking to a passenger. There is no difference. And so those 15 people who failed to stop would have failed to stop regardless of what treatment group they were in. And so essentially that there is no difference or no effect of talking on a cell phone versus talking to a passenger. And then just by dumb luck, of those 15, we got 12 assigned to one group and 3 assigned to the other, right? So how likely is that to have happened? And so what we're going to do is we're going to look at, well, there were 33 people who stopped and 15 people who did not stop. And so we want to look at a deck of cards and try to simulate this situation. So if you take a standard deck of cards and you remove 1 ace and you remove 3 2s, so you have 1 2 left in the deck, and you have 3 aces left in the deck. Everything else is the same, except, of course, we take out the jokers because we're talking about 52 cards. So if we do that, we take out 1 ace and 3 2s. We've removed 4 cards, so we have a total of 48 cards. So you can see that 48 cards corresponds to the 48 people. Each card represents 1 person. Okay, so all of the 2s and 10s, that's 33 cards, those represent the people who did stop at a rest stop. And then the face cards, which are Jack, Queens, and Kings, that's the cards that have faces. And then also the 3 leftover aces, those are 15 cards. And those will represent the people who did not stop. Okay, so you're going to take your deck of cards, you're going to shuffle them, and you know, maybe a couple times, and you're going to divide, you have 48 cards now, you're going to divide those into 2 piles of 24, randomly assigned. So 1, 2, 3, 4, you're going to just keep doing this until you get 24 cards in each pile. And then at which point you're going to pick up one of the piles, and then you're going to count. In that one pile, we're going to call this the cell phone pile. I pick it up and I count how many face cards or aces. That's the people who did not stop. And you're going to write, you would write down that number. So, and you could do that again and again. So you're going to count through and say, oh, I got 6, let's say, 6 faces and aces in my one pile that I picked up, which is my, cell phone treatment pile. And then you're going to repeat that step. You're going to, okay, so put all the cards back together, and then you will put them all together again, and you'll shuffle, and you'll do that again. And so we'll do that again and again, and we'll see how often we get 12 or more of the faces and aces, that's the non-stopping people, to be in my cell phone group. So do that a couple times, write down the numbers. Now, if we were in class, I would have you yelling out these numbers, and I would be creating a dot plot on the board. You can see here I've got the dot plot data in a dot plot from a previous year. And so you can see it's fairly normally, it looks like it's kind of potentially normally distributed. It certainly seems to be, a bell shape and kind of looks normal. All right, so according to our simulation in this case is 106 data values, and I plotted them using some software. What we want to do is, according to our simulation, what is the probability of getting 12 or more of the 15 non-stoppers, that's the aces and faces and aces, non-stoppers in the cell phone treatment group, in the one pile that we picked up. So you can see, if we look, we have, there's 12. That's the result, right? They got 12 in one. So we didn't get any in 12. But remember, this is going to generally be thought of as a normal curve. And so it's a density curve. And so we can't calculate probabilities of a particular value, but a range of values. So we want to say, what's the probability that we got 12 or more of the non-stoppers randomly assigned to the cell phone treatment group? Or in other words, according to our simulation, what's the probability that we got 12 or more aces or faces in our cell phone pile that we picked up and counted? And so we can see here that we only got, in this particular simulation of 106, we only got one occurrence of 12 or more, that one out there, that one dot at 14. So the probability of that getting that, a simulated probability of that getting that, is 1 out of 106, and that's less than 1%, just shy of 1%. So that's 0.0094, so just shy of 1%. Now, we talked earlier about, okay, so the probability of this happening just by chance, because that's what our simulation is, it's just by chance. So the probability of that happening just by chance is pretty small, less than 1% chance. And so our threshold is 5%. So if it's less likely to occur 5% of the time just by chance, and that's of course what's happening here, it's actually less than 1% chance that it would happen just by chance, we will call this result statistically significant. It's not very likely to have occurred just by chance, so it probably didn't occur just by chance. And what's really happening here is that there's an actual difference in the treatments. The treatment of listening, listening and talking to a passenger versus using your cell phone, there does appear to be a significant difference in the attention of a task. In this case, the task was pulling off into the rest stop. All right, so your homework for this section is listed here. So number 67, number 70, number 72, and number 74. That will be due next class.